Right, the topic of today is graphing quadratic functions in what we call vertex form. We're going to use the same transformations or walking at home principle that we've applied to linear functions and absolute value functions. But before we go any further into the procedures, I just want to remind everybody that what we're trying to do when we graph a function is to demonstrate where all of the solutions to the equation exist. For example, if x is equal to 1, then we can find f of 1, and that would be 1 plus 2 squared plus 5, and that would give us 3 squared plus 5, which is 9 plus 5, or 14. Not so good with numbers. The point is, that's literally a point, that is when x is 1, y is going to be 14. Remember, 114 is a solution to the equation because when x is equal to 1, y is equal to 14. Now we can find infinite solutions to this equation by putting in as many different values for x that we can dream up. There are infinite x's to choose from, therefore there are going to be infinity different y values that are going to result when I put them into this equation. For various reasons, which will become more apparent as you proceed through mathematics, for various reasons, being able to present all the solutions to an equation in graphical form turns out to be a pretty handy technique. So the procedure that I'd like us to follow is no different than what we've done in the past with other functions. First, we're going to visualize what should be happening to the general parabola. Where are all the solutions going to lie, and how are they going to compare to the original y equals x squared? So I know that this function is going to shift to the left 2 because of the addition of 2 before I square. The graph is going to shift up 5. The a value is implied to be equal to 1, so there's going to be no stretching. It'll be the standard shaped parabola. So to imagine what that's going to look like in my mind, I just visualize this sort of parabola. Then my goal is to make it happen. So after setting up my grid using a ruler, I verify where the axis of symmetry is, and the axis of symmetry is always going to be the x value of the vertex. I plot the vertex, and in this case it's going to be from going left 2 and up 5, negative 2, 5 will be the vertex, and I'm going to draw a standard parabola from that point. So I'm going to first go over 1, up 1, that's the a value, and put my next point there, and then I'm going to go 2 away from the vertex. 2 squared is 4, so I'm going to go over 2, up 4, and so that's how the typical parabola is going to look. All I have to do now is do the same thing on the left side. In other words, I use my symmetry, I don't even have to think as much, and I get the other 2 points. These 5 points will guide the drawing of a parabola. Label these key points, because these are the ones that help me draw the parabola. I label them, I label the axis of symmetry, and I can check in 2 different ways. I can pick one of my points, an interesting one, non-vertex, and verify that it is a solution to the equation. Remembering again, all of these points are significant because every one of these points has an x and a y, which collectively represent solutions to this equation. This is one of the solutions, negative 4, 9, as I claimed, and to verify it is indeed a solution to the equation. Don't forget, use technology just to make sure that everything is the way you believe it is. Sometimes we can trick ourselves into believing something that's not true. For example, we could move this right 2 and up 5 and draw our parabola in the first quadrant. And then if you check your point, you could convince yourself that you were right just by dropping a negative. But by putting this into a graphing calculator, we can now verify that the solution set looks very much like the solution set that I drew here. Quickly through another example, just because now I've changed the a value and we have to figure out how to deal with that. So I know that the parabola shift from the origin right 2 and down 1. That's the easy part, but then what about the negative 3? After I square my numbers, I'm going to multiply them by negative 3. What's that going to do? It's going to have the effect of stretching by a factor of 3, so we've observed that behavior when exploring Desmos. It's going to be stretched out or elongated in a vertical fashion, so I say stretch by a factor of 3, and then the negative is going to cause a flip. The correct word is reflection, and that is to say, if you use the phrase opens down, then everybody in the math community knows you mean a parabola whose opening is pointing downwards. The vertex is at the top. So I envision moving right 2 and down 1. I envision a stretched out parabola that opens down. Now to make it happen, I plot the vertex. From the vertex, I go over 1, down 1. So this is, well, normally I would go over 1, down 1, but because a is equal to -3, I'm going to go over 1, down 3. So 3 times as much as I used to because I'm multiplying everything by 3. And instead of going up, we go down because of the negativity. Once again, I used to go over 2, down 4, actually over 2, up 4, but now I'm going to go over 2, down 4 3 times. So there's 1 4, 2 4s, and 3 4s. Means I got to count all the way down to -13. Using symmetry, I can find the other 2 points, and then I just have to draw the parabola after I label everything, of course. And there we have it. So again, matched up with technology. Again, we can verify in a variety of different ways. So I hope this makes it easy. This is pretty straightforward stuff. Just practice so that it becomes second nature, and you'll find in the later lessons how this skill can benefit you.